Let's derive the equilibrium equations for a continuum. And the basic assumption of a continuum is that it's infinitely divisible. So in other words, matter fills the entire space that it occupies, which is what we see at the macroscopic level. So the equilibrium equations that we're going to derive here apply to solids and also fluids. So consider this solid body that's loaded at different positions and also restrained at different positions. So this body is going to deform under these applied loads. And if we cut out an element from the body, we expose the stresses acting on this element. Now applying Newton's first law in the x direction, where the sum of forces are equal to 0, we have the following stress on this face, which is at a distance delta x from this point. So basically, to get that stress, we'll just do a linear Taylor series expansion about this point, which we'll call x0, y0, and z0. And this is at the face where this stress is acting. So what we have is this stress is sigma xx plus the partial derivative of sigma xx with respect to x by delta x, and then minus sigma xx multiplied by the area on which these stresses are acting, which has an area delta y by delta z, gives the net force in the horizontal direction due to these axial stresses. And similarly, we have tau yx dash acting in the horizontal direction. So again, doing a Taylor series expansion, we have tau yx plus the partial derivative of tau yx, this time with respect to y, and that's multiplied by delta y. So again, we did a linear Taylor series expansion about this point. So we're neglecting higher order terms because they disappear in the limit when the volume of this element approaches 0. And then we subtract tau yx on the other side, and that's multiplied by the area of the face on which it's acting. So that will be delta x by delta z. And finally, we have tau zx dash, which is tau zx plus the partial derivative of tau zx, this time with respect to z. So we have tau zx acting on the back face, multiplied by delta z minus tau zx, and that's multiplied by the area on which these stresses are acting, which is the z face with an area delta x by delta y. And the net force by Newton's first law is equal to 0 in the horizontal direction. And now we can cancel out the stresses, and we also have delta x by delta y by delta z for each of these terms. So we can cancel these out also. So what we're left with are the partial derivatives, which we'll write down here. And similarly, if we took an equilibrium of forces in the vertical direction, we'd have a partial derivative for tau xy with respect to x, which, as we can see, we have an opposite stress acting on the other side. And then we have a partial derivative of sigma yy with respect to y, and then plus the partial derivative of tau zy with respect to z. So as we can see, these are the stresses that are acting in the vertical direction. And similarly, an equilibrium of forces in the z direction gives a partial derivative for tau xz with respect to x, and a partial derivative of tau yz with respect to y, and a partial derivative of sigma zz with respect to z. So these equilibrium equations can apply to different continuous bodies, including solids and fluids. And we'll use these in our torsion problem.